Okay, so final speaker of this session is João Luís Rosa. He's going to tell us about testing the hypothesis of the bosonic star at the galactic center. Please start.
Thank you very much. So my name is João Luís Rosa. I am a postdoc researcher at the University of Tartu in Estonia. Today I'm going to speak about, as it was presented, testing the hypothesis of a bosonic star at the galactic center. This is a work I've been doing in collaboration with Professor Vítor Cardoso in Lisbon, Professor Paulo Garcia in Porto, and also Frederic Vincent, which is at the Observatory of Paris right now. We still haven't uploaded the draft for this paper, but most of the essential information is on the poster. So in the end, if you find this work interesting, I'll give you my email. Please feel free to send me an email, and I will share the poster with you so you can see in a broad way what was done and all the essential details per se. So let me start by motivating my work. So today, today we have observations indicating that objects behaving like the predictions for black holes exist in the universe. In particular, there are two important recent observations that are the orbits of stars near the center of the Milky Way. This was detected by the ESO. And also more recently, even the observation of the first black hole shadow at the center of galaxy M87. And these two observations, they are in agreement with the predictions of general relativity for black hole spacetimes. Now, the problem is that although black holes seem to be consistent with all of these observations, we know from the mathematical point of view that black holes do have problems. Black holes have singularities, black holes have event horizons, black holes are associated to information loss paradoxes. So although they can explain all of these observations, they still carry problems in themselves at the fundamental level, problems that we don't really understand and don't really know how to deal with. So it would be very important if one could somehow develop a model for some kind of compact object that somehow is able to reproduce precisely the same observations, but with the advantage of not having event horizons nor singularities, right? So this is the main objective of our work, is to try to develop an alternative, or to take models that already exist and test them against observations and eventually prove or disprove that these objects can substitute black holes in this particular case. Now, the problem is that if you are trying to take some exotic compact object and replace a black hole with this object to reproduce the same observations, sometimes it's not easy to take a conclusion. For example, for this case of the S2 star orbit, this star is orbiting very far from the black hole, very far in terms of geometrized units. So for example, this star is orbiting at a radius of hundreds, thousands times the mass of the black hole. So they are very far. So even if you change the black hole spacetime by some other exotic compact object, in principle, if you are far from the object, the solutions are going to be exactly the same. So these kind of observations is not useful to test if the model is a black hole or not. You need something that's closer to the horizon. Now, black hole shadows is a very nice point. In here, we are close to the light ring. We are close to the center of the distribution of matter. So in principle, one can use these observations to test if the object in the center is a black hole or not. But in this work, we are going to use none of these observations, but another recent observation also made by the Gravity Collaboration in 2020. So what the Gravity Collaboration has detected are infrared flares very close to the center of our own galaxy. And as you can see, so what we have here is the points where these flares were observed near the center of the Milky Way. So this is in units of micro arc seconds. And you can see that the radius, this R here is the radius of the radius of the orbit. So there's some kind of thing emitting infrared flares orbiting near the center of the Milky Way. And what you can see is that the radius of this orbit is of the order of between 7 and 10 M. So this is really close to the innermost stable orbit. And so this is really close to a point where if the object is not a black hole, you can really observe the differences between the spacetime of a black hole and the spacetime of an exotic compact object. So this is what we're going to do. We are going to take these observations. We are going to model what would be the observations if the central object was not a black hole, but some kind of exotic star, in this case, a boson star or a Proca star, and see if this is compatible with the observations from the Gravity Collaboration. This is the main objective. Now, In this particular work, we are interested, as I said, in bosonic stars. Bosonic stars can be of two types. They can be scalar boson stars or vector boson stars. The first ones, the solutions for scalar boson stars or boson stars made of a scalar field, are localized solutions of complex scalar fields in the Einstein-Klein-Gordon theory. So this is the Einstein-Klein-Gordon theory. We take general relativity and we add a complex scalar field. Now notice that this representation of the theory is the most possible, the simplest possible theory in the Einstein-Klein-Gordon theory that is of interest for us. Because as you can see, the potential here is simply a mass term. So this is a massive scalar field and that's all. We could make more complicated solutions by adding higher order terms like 5 to the 4th, 5 to the 6th, etc. But for starters, let's take the simplest possible solution, which is just a simple massive scalar field, and see what happens. Now for the Proca stars, so stars, self-gravitating stars made of a massive vector field, the idea is very similar, but instead of adding a scalar field, you had a massive vector field. This is called the Einstein-Proca theory. Again, you take general relativity and you add a massive vector field. Again, the potential is the simplest possible, just a mass term. And in here, this tensor F is simply the electromagnetic tensor associated to this vector field. So you compute the equations of motion. This is the Klein-Gordon equation, the equation of motion for the complex scalar field in the Einstein's Klein-Gordon theory. And this is the Proca equation, which is the equation of motion for the vector field in the Einstein-Proca theory. So what we need now is to insert a general form of a spherically symmetric and static metric and compute what are the solutions both for the metric and for the distributions of the vector field and the scalar field. And in particular, we want our solutions to be localized. Localized means two things. First thing is that the solution must be regular at the origin. So unlike black holes where the metric diverges at the origin, now we want something that is limited, it is finite at the origin. We impose this kind of regularity. And the second thing we need is that the solution decays exponentially when one is far away from the central object. So this guarantees that the solution is localized in a finite region of space, which is precisely what we are looking for. So let us make our ansatz. Let's take the most general metric that is spherically symmetric and static that we can imagine. This is our result. We insert this metric into the field equations and into the equations of motion for the scalar field and the Proca field that I showed in the previous slide, and we get a set of 3 coupled differential equations, 2 field equations and 1 equation for the bosonic field. Now these 3 equations are coupled, so we have to solve them all at the same time, and usually we have to solve them with numerical methods because the equations are really complicated. So what we do is to recur to shooting methods. To do so, we need to introduce an ansatz for both the scalar field and for the vector field. So this is the ansatz we choose. Now notice that I said the solutions are going to be static, but if you look into these ansatzes, you will see that there is a time dependence, this harmonic time dependence. And here and the same thing for the vector field. Now, even though the scalar field depends explicitly on time based on this ansatz, the solutions will still be static. And this happens because if I go back to the previous slide, notice that how all of the times the scalar field and the vector field appear, there is a complex conjugate that is able to cancel the time dependence in the scalar field or in the vector field. So even though the scalar field and the vector field depend explicitly on time, the solutions will still remain static after we obtain the solutions. So what we do again, we use the shooting methods to find the solutions for the scalar field and for the vector field. In here, the scalar field, the solution for the scalar field is simply computing the solution for this function psi here. For the case of the vector field, we need to find the solution for both this function f and this function g. But after we have these solutions, we have the solution for the scalar field and the vector field, and we also have the associated solutions for the metric, which is pretty much computing the solutions for this function u and for this function lambda, which are basically the GTT and the GRR. So once we solve these equations numerically, we have the entire solution that we need. So let me show you the solutions for the scalar field and for the vector field. Here on the left, we have this gamma represents the density of the scalar field as a function of the radius. And I have plotted 4 different solutions. Now this parameter gamma 0 is the central density of the scalar field. So as you can see, for example, 0.4 is here, 0.4, 0.25 is 0.25, etc. So this corresponds to the central density. we take the central density, we make the integration, and as you can see, what I said before, we want the solutions to be localized. This is verified in here. All the solutions decay exponentially at large radii, so this guarantees that our scalar field is localized in a finite region of space, which is precisely what we are looking for. Now, why did I choose these 4 values here? This is not arbitrary. When we want to take a numerical solution for a boson star or for a Proca star, the value you choose for the central density will correspond to a value of the mass of the boson star and consequently to a value of the radius of the boson star. Since one of the things we want to do is to impose constraints on the possible radius of this boson star, we choose 4 different values of the central density, which will be associated to boson stars with 4 different radii. For this first boson star, the radii is equal to R equals 9m. For the second boson star, R is equal to 12m. The third one is R equals 15m. And the final one is R equals 20m. So each of these solutions corresponds to a boson star with a different radius. Now, this is the solution for the scalar field, and it is also the solution for the first function. Qualitatively, it's the same solution for the first function here in the vector field. And this happens because, as you can see, the ansatz are pretty much the same. Now, for the function g, this function here, the solutions are slightly different. This is what we obtain. But once again, we choose 4 different values of this F0. This F0 is the central density for the function f, which is the central density of the Proca star. Notice that this solution is only for the Proca star. And we choose, again, 4 different values to guarantee that the radius, the radii of these Proca stars are, again, 9m, 12m, 15m, and 20m. And these are the solutions we obtain. Now, we have the solutions for the scalar field and the Proca star, for the scalar field and the vector field. Since all the equations are coupled, when you find these solutions for the scalar field and for the vector field, you are at the same time obtaining the solutions for the metric, this nu and this lambda. So let me show you what are the solutions for the metric associated to these distributions of scalar and vector fields. So for the boson star, this is what we find. On the top plot, we have GTT, and on the bottom plot, we have GRR. Again, for the same 4 solutions that were plotted before. And in here, we have this black line, this thin black line corresponds to the Schwarzschild solution. So as you can see, these are the main differences we are looking for. First of all, this solution is regular at the origin. So unlike the black hole solution that diverges at the origin, these solutions attain a finite value at the origin. And in particular, the GRR goes to 1, goes to 1 at the origin, precisely what we're looking for. And depending on the value of the central density, which corresponds again to depending on the radius of the boson star, the solutions will be more or less similar to the Schwarzschild solution as one goes further away from the center. For example, remember that this first boson star corresponds to a star with a radius r equal 8. If you go to this plot to r equal 8, you can see that at this point or after this point, this solution is pretty much indistinguishable from a Schwarzschild black hole. And the same thing for the other. So for example, take this one, gamma 0 equals 0.12. This corresponds to a star with radius 20. If you go to radius 20, you can see that this star is indeed pretty much indistinguishable from a black hole at this point. And this is caused precisely by the fact that the the boson star is collapsed in the finite region of space. So if you are further away from the center than the radius of this boson star, the solution is indistinguishable from Schwarzschild. And again, we get to the same problem as before. And the same thing can be seen from the GTT, from the GRR. Again, if you are in a radius smaller than 20, you can see that there is a discrepancy between this red line and the boson and the Schwarzschild solution. But if you are close to 20 or after 20, this red solution is pretty much indistinguishable again from the black hole solution. So this is precisely what we mean by localized. For the Proca star, the solutions are qualitatively the same, so there's not much to say. Again, we choose the values to guarantee that the radii of these boson stars are the same. And you can see that the distributions and the qualitative behavior is the same. If you are in a radius that is smaller than the radius of the Proca star, there is a discrepancy between the black hole solution and the boson star solution, or the Proca star solution in this case. But if you are further away from the radius of the Proca star, you see that the solutions are pretty much indistinguishable. So what is the consequence of this? Well, the main consequence is that if I now take an object and I put an object orbiting a central boson star or central Proca star, well, there's going to be differences in the orbital period and in the orbital velocity compared to a black hole, right? So this is the results we have for, these are the results we have for the orbital velocity and the orbital period. So again, let's start with the boson star. Here on the left, we have the orbital velocity of a certain object around a central boson star, again, for the same 4 boson stars that we had before, as a function of the radius, starting at the ISCO. And again, we can see that if you choose a radius that is smaller than the radius of the boson star, there are measurable and observable differences between the orbital periods of an object going around the central black hole or central boson star. But if you go to a radius that is big enough, large enough, then the orbital velocity becomes indistinguishable from a black hole or from a boson star. So if one is able to measure what are the orbital periods and the orbital velocities of these infrared flares around the center of a Milky Way, then one can infer, is it possible that the solution is not a black hole, but a Proca star or a boson star? And if so, we can impose limits on the radius of this boson star or Proca star in the same way. Now, on the bottom plot, what we have here is the difference between the orbital periods for boson stars and black holes divided by the orbital period of a black hole. So you can see that if you are very close to the ISCO, again, this plot starts at the ISCO. If you are very close to the ISCO, you see that orbiting a black hole or orbiting a boson star, the results are different for the orbital period. By the way, this black line here represents the 1% difference between the period in a boson star and the period in a black hole. But as you move further away from the center, from the ISCO, you see that these discrepancies in the orbital period decrease, and eventually they are smaller than 1%. So if the error bars, if the errors in the observation are of the order of 1%, and they are not, they are bigger than that, but if they were of the order of 1%, then you could actually impose limits. If you measure the period, you could impose limits again on the radius of a boson star based on this observation, based on these calculations. Once again, I'm not going to waste too much time on this, but the results for the Proca star are qualitatively the same. There are some small differences. In particular, these differences are mostly noticeable for the bigger Proca stars. So, for example, in here we see that the derivative of the orbital velocity at the ISCO is negative, whereas in here it's not precisely 0, it's still negative, but it's way smaller than for the case of the boson star. And also for the differences in the orbital period, we can see that although for boson stars, for the biggest one, so R equals 20, the orbital period decreases in this way, the decrease for this larger bosons, the larger Proca star, is slightly different. It still goes to very, very small values, but not as quickly as it happens for the boson star, in particular for the biggest solution, for the solutions with larger radii. Now, these are all just calculations one can do by knowing the matching and by knowing the distribution of the scalar field. But now we want to do something to compare with the observations for by gravity. So the observations for what it looks like at the center of our galaxy. So to do the next step, we are going to use a numerical code. This is called GYOTO. It was developed by, one of the developers was actually my collaborator, Frédéric Vincent at the Paris Observatory, but there are more collaborators. And what this code does, this is a ray tracing code. And what it does is pretty much to integrate photons on a given angle of view and produce images of what it looks like, of what a given system looks like at in that distribution. We implemented these 4 boson stars and these 4 Proca stars in the code, and we simulated what would look like for a spherical isotropically emitting star orbiting a central boson star and a Proca star, and comparing this with what happens for the black hole solution, so we can have a qualitative idea of what the differences are. So these are the results. In here we have the first one is the boson star, what happens for a boson star. This one is the Proca star, and the one in the bottom is the Schwarzschild solution. Now, what's happening here, what's happening here is we have this spherically emitting object here, and the object is making an orbit around the central boson star, Proca star, or Schwarzschild black hole with a radius r equals 8m. The orbital radius is r equal 8m. The radius of the boson star and the Proca star is r equals 9m. And we are observing this system from an inclination of 80 degrees. So the equatorial plane is more or less like this. And then we are looking at this system at an angle of 80 degrees. Now, what do we see? We see more or less what's expected, right? If the object is in front of the boson star, then there's pretty much no distortion. We see the photons coming directly at us. But when the object starts moving to the behind of the boson star, the Proca star, we start seeing some distortions in the image. Eventually, there is a secondary image appearing. Let's look here at the Schwarzschild black hole case, for example. When the object is moving behind the black hole, the primary image gets distorted and the secondary image appears. Here it is. And when the object arises on the other side, the secondary image disappears and we recover what we have seen before. Now, for the boson star and the Proca star, there are very important differences in this. And I think the most noticeable difference is the fact that instead of only having a primary and a secondary image, we have 3 images. Let's look at the Proca star here, for example. The object is moving behind the Proca star. First image starts getting distorted, and out of nowhere, we have not 1, but 2 secondary images appearing here. And the same thing for the boson star. Can you see it? So there is a very important observable difference between what happens for the boson star and what happens for the Schwarzschild black hole. And the same thing, Proca star versus black hole. There is not only an extra image, but there are the differences, like the distortion in this primary image is different, the deflection angles are different, but then again, the most important difference is the fact that there appears a third image in the system. So one question one might ask is, where does this extra image come from? We know that in the case of Schwarzschild, there is a primary image caused by photons, especially if you are looking at the system in an inclination of 80 degrees. There are photons arising to the observer, moving, being deflected above the black hole. There are photons arising, being deflected below the black hole, and this forms the two images, the primary and the secondary. In the case of a boson star and the Proca star, and pretty much any other object that doesn't have an event horizon, there is a third image appearing. And what does this third image correspond to? Well, it corresponds to objects crossing the interior of the central object. This cannot happen in the Schwarzschild black hole or any kind of black hole because of the event horizon. If a photon tries to cross through the Schwarzschild black hole or any other black hole, it gets trapped inside the horizon, so it doesn't work. But for a boson star and the Proca star, this works. To prove this to you, to prove that this third image actually corresponds to photons coming through the object, I'm going to show you a plot of 3 different geodesics computed for a given image. So this is, again, a boson star. At a certain instant, we paused that video in a very precise instant of time that guarantees that we have 3 images. So this is the primary, the secondary, and this one that comes through the center, which is still a secondary image, but passes through the center of the black hole. And we have chosen 3 pixels in this image. 1 pixel in the primary, 1 pixel in the secondary, and 1 pixel in this one in the middle. This is a 50 by 50 image. The images before were 400 by 400, so this is why this one is a little distorted, but the idea is pretty much the same. It's the same solution. We just made a video 50 by 50. We paused the video at a certain instant of time where we have 3 images, and we compute the geodesics. So for the first geodesic, this is what we have. So this is a plot of the z-axis, so the vertical axis, the axis of symmetry for the orbit, and this is the radius of the orbit, or the radius of the geodesic. Since our object is orbiting at the equatorial plane at the radius r equals 8m, we know precisely where our object is. The object is here. This is equatorial plane, z equals 0, and radius equals 8m. So we can see that this object arises, the photons emitted by this object arise to the observer by moving above the black hole, or in this case, above the boson star. They go to a positive z, they never cross the equatorial plane again, and they asymptotically reach the observer. Now, for the secondary image, it's also pretty much what we are expecting. We know where the object is. Again, equatorial plane, radius equals 9m, so the object is here, emitting. The photons are emitted, in this case, to a negative z, and then they are deflected. They cross somewhere in this point, they cross the equatorial plane again, and eventually they reach the observer asymptotically, precisely at the same angle. Now, what happens for this image in the center? Well, as we expected, the object, again, I emphasize, equatorial plane r equals 8, the object is here, and now let's follow the geodesic all the way up to the observer. What happens? Well, the radius of this geodesic, as you can see, it gets really, really close to the center, and it almost touches r equals 0. If this geodesic is crossing r equals 0 and z also approximately 0, this means that this geodesic is crossing the interior of a sphere which radius r equals to m. So in the case of the boson star and the Proca star, there is no problem. This geodesic just crosses the center and eventually reaches the observer again. But if this was a black hole, this photon would be immediately trapped inside the event horizon. So this is precisely the main reason why for any exotic compact object that doesn't have an event horizon, we see 3 images instead of 2. And this is the main difference between the images of these 2 systems. And it is a very important observer that can be used to test if the central object is indeed or not a black hole. Now, there is one more thing that is comparable to between black holes and boson stars and Proca stars. This is the integrated flux. What is the integrated flux? The idea is very simple. Take the videos I've shown you before. These videos, for each instant of time, they have the emitting observer, the emitting object at a given point, and we have the observer watching the system. This observer at this particular instant gathers some flux from all the pixels that you see there, the pixels where the photons are coming from. We sum the pixels, and this corresponds to the magnitude of the object at that precise point. The integrated flux corresponds to the sum of all the magnitudes around the complete orbit. So if you integrate the flux for all the points in the orbit, this is precisely what you see. So this is for the Schwarzschild black hole here. This is for a boson star with radius 9, and the results are pretty much self-explanatory. So when the object is crossing in the front of the black hole, we see a single image. When the object moves to the behind of the black hole, the primary image gets distorted. This is what this region here is. And when this happens, there is a secondary image appearing in the bottom of from the bottom of the black hole that corresponds to this line right here. Notice that this line does not intersect itself. It starts here and it finishes here because the secondary image appears at some point and disappears at the other, and there's nothing in between because there is an event horizon here. For the case of the boson star, this is different. We have the object crossing in front of the boson star. When it goes behind, it gets distorted. The secondary image appears that corresponds to this line below. But since we also have a third image appearing, and this third image, if you remember from the videos, this third image crosses the field of view horizontally in the center, then this is what you see. So this line here, it is a closed line instead of an open line because the secondary image breaks into 2 and then glues together again on the other side. So again, there are obvious differences, visible differences in the integrated flux between Schwarzschild black holes and boson stars. Now, this is the result for a boson star of radius 9. And the question is, what happens if we change the radius of the boson star? And this is what happens. So in here, this image, the first image is precisely the same as this. And the following images correspond to the 3 other boson stars we have computed. So first one, radius equals 9, then radius equals 12, radius equals 15, and radius equals 20. So there are, again, differences. Notice that only for the first 2, we have a secondary image appearing. And why is that? Well, this is because if you go to a boson star with radius 15 or with a radius 20, the boson star is so big, the mass is so dilated from the center that the object orbiting at the radius equals 9, the mass inside its orbit is so small that there is not enough gravity to deflect the photons and create a secondary image. So if you observe the center of the Milky Way and you see the size or the trajectory of the secondary image in your field of view, the differences in this trajectory of the secondary image may give you a hint on the radius of this boson star. Or Proca star, the same thing, the results are qualitatively the same. And if you do not see a secondary image, then this means that the boson star can be very, very dilated. If you don't see a secondary image, then this seems to impose that a solution cannot be a Schwarzschild black hole, because in the Schwarzschild black hole, you are expecting a secondary image, whatever the mass of the black hole is. Finally, one last thing before I stop my talk. There is another thing that can be comparable. this is the, as I said before, for a given instant of time, you receive a certain magnitude from the the field of view, and you can do one more thing. You can compute the centroid of your observation. So what is this? What is the centroid? So imagine that at some instant in time, you only have one image in your field of view. Then all the photons are coming from that precise image, and you know that the centroid of your observation is that image. Now, when the object moves behind the boson star or the Proca star, and the secondary image appears, you have a bigger magnitude because you are receiving more photons than before. So you have now two images in emitting photons to the observer. So the magnitude increases. But furthermore, since now you have two images that are not in the same place, then the center, the geometrical center of your observation is moved to a different place, right? And this is also something that can be detected by the gravity instrument. So let me give you some examples. These are simulations for different inclinations. So this is 20 degrees, 50 degrees, 80 degrees, and 90 degrees. We again have an object in the equatorial plane, but now let's say that the object has different orbital radii. The blue line corresponds to a radius, orbital radius r equals 8. The yellow one, r equals 10. The green one, r equals 12. And finally, the red one is r equals 20. So you put your object orbiting around the central boson star. These results are for the boson star, which radius equal 9. And you see what is the magnitude and what is the centroid. So for example, for I equals 20, inclination equals 20 degrees, you can see that for these three inner orbits, the centroid is pretty much a circle. It's not really a circle because inclination is not 0, but it's pretty much a circle. And this means that there is never a secondary image appearing in your field of view. You are always following the primary image at every point, and nothing strange happens. And this can also be seen here from the normalized magnitude. There is an increase in magnitude at some point. This corresponds to the Doppler shift when the object is moving in your direction. And this one corresponds to the Doppler shift when it's moving away from you. But there's nothing special appearing in the image. Now, if you choose an orbit that is way wider, for example, r equals 20, you can see that the centroid of your orbit at some point moves from this outer radius. What does this correspond to? Well, when your object is here, there's only one primary image. The object goes all the way around and there's just one image. But at some point, when the object reaches this point, there is enough deflection from your field of view. Remember that you are watching this from 20 degrees inclination. There is enough deflection at some point to create a secondary image on the opposite side of your field of view. So when this secondary image appears, the centroid of your observation is moved away from this outer radius to some point closer to the center. And when the secondary image disappears, here we are, we again recover the outer orbit. Now, this also has implications in the magnitude. As I said before, if a secondary image appears in your field of view, then you are receiving more photons than you were receiving when you only had a primary image. And this is clear here in the normalized magnitude. So the magnitude follows a curve very similar to the other quantities. Can I zoom this up for a while? Yes, I can zoom. So you can see that the red curve qualitatively is pretty much the same as the others, but there is some point here where the magnitude increases and then decreases again. So this corresponds precisely to the time interval where a secondary image appears in your field of view. There is an increase in magnitude caused by the secondary image, and then when the secondary image disappears, you recover just the expected line where no secondary images are. If you repeat this process for other inclinations like 50, 80, and 90, you can see that you can have these discrepancies in the centroid, in the magnitude at different radii. Notice that for a small inclination, you can only see this discrepancy for the widest radius, so radius equals 20m. But if you move to bigger inclinations, you can see that all of the orbits, even the smallest one, which is a radius equal 8m, all of the orbits, they have this effect. So for example, take the blue orbit. Let me zoom in a little bit here. Here we are. Let me take the blue orbit. When the object is in these positions right here, you only have a primary image, nothing strange happens. And when the object reaches this point, a secondary image appears in the opposite side. And so the centroid moves closer to the center of the image. And then the secondary image is present. When the secondary image disappears, the centroid moves back away to the primary image. And again, we can see this effect also in the magnitude. So the magnitude is following pretty much the same curve as before, but at some point for the blue curve, at some point, a secondary image appears, and this corresponds to a peak in the image. Here it is, and then it follows this line here. And finally, when the secondary image disappears, this peak decreases again, and we have something that follows the expected line as before. In this case, the amplitude of this magnitude is bigger than before, because since we are looking at the system from a bigger inclination, then what happens also is that the Doppler shift is also bigger. And so this is why the magnitude here, the maximum of magnitude here is bigger than the maximum of magnitude here, but it's pretty much the same effect. Let me zoom out again. Yeah, okay. For 80 degrees, again, same thing happens. Secondary image appears, secondary image disappears, and the magnitude is even bigger because now we have a bigger Doppler shift. For 90 degrees, we have this huge peak right here. And this peak right here corresponds to the point where the object is precisely on the opposite side of our field of view from the observer. And what we see here is pretty much the Einstein ring. And this is why we get photons from so many directions, then the magnitude sees this peak. So I'm almost concluding. Let me just give you a brief review of what's done so far and what's going to be done next. So as you have probably noticed, all of the work I've done here is pretty much theoretical. We have developed the models. We have implemented the models in the numerical code. We have traced simulations. We have computed all of the predictions if the object in the center is a boson star or a Proca star, but we still need to compare this with experiment, right? We have developed the framework that produces our predictions, and the next step is to compare with experiments. So what do we expect from comparing with experiments? We have observations from the orbital period, we have observations from the centroid, and we have observations from the flux. These are three things we can compare. And using these comparisons, or making these comparisons between the observations and our predictions, we can impose constraints on the radius of the stars, eventually on the masses of the stars. And since the masses of the stars are directly associated with the mass of the scalar field and the vector field, we can also eventually impose constraints on the masses of scalar fields and vector fields. So if one has, let's say, a dark matter candidate for a scalar field or a vector field, these effectively can impose also constraints on the mass of these fields. There is one last thing we wanted to do, which was to test the validity of Newtonian approximations. There is an advantage in Newtonian approximations, which is the fact that we can, with only one implementation, have a full range of possible masses for a boson star or a Proca star, whereas in the case of numerical boson stars and Proca stars, every time we need a different radius, we have to implement a new boson star. So there is an advantage, but we are not sure if the Newtonian approximation is valid in this environment, because we are so close to the center, the strong field, we are in the strong field regime. So it's not obvious if the Newtonian approximation is valid or not. So this is something that we also wanted to do, and we are in process of doing that. Thank you very much. And again, I'm going to show you my poster. My email address is right here. If you are interested in knowing more, please send me an email and I will share the poster with you. Thank you very much.
Joe, thank you very much for your nice talk. And question and comment? Shinji, please.
Yes, thank you for the nice talk. So do you expect that boson star or Proca star at the center of galaxy, if they are rotating or non-rotating?
In principle, it's going to be rotating, of course, but the problem with boson stars and Proca stars is that when you impose rotation, especially in these most simple models, they become unstable. So all of this work, you can think of this work as let's say a toy model, a first step towards more relevant and more physically relevant solutions. So we started with the most basic thing possible, just mass terms. We implemented and we tested. Of course, we are aware that this is not the most physical solution because we expect the central object to be rotating. And of course, this is only one of the various approximations or the various assumptions we did. So there is staticity, there is spherical symmetry, which immediately disappears if the object is rotating. But there are other things, like, for example, we did not model accretion. We did not model an accretion disk around the center. We did not model eventually some accumulation of mass in the center. So there is a lot of things that are still to do. This is just, let's say, first step, toy model. Let's see if this works. And if it does, then we move to more complicated models, more physically realistic models.
Okay, yeah, thank you.
Thank you for your question.
Any other question or comment? Okay, I have a question. So what is the essential difference between boson star and Proca star?
Well, the difference is just the fundamental field that that is in that is creating, that is self-gravitating to form this solution. So in the case of a boson star, yes.
As a star, what is the crucial difference?
The observations will be different. So, for example, let me zoom in a little bit here. So, I think if I understood your question, you want to know what's the difference if I have a boson star or a Proca star, and the differences are in the observations. So, all the observations I have put in here, and also in my talk, these observations for the integrated flux and the magnitude. These are the observations, or let's say the predictions for a boson star. If you have a Proca star instead, there are slight differences. For example, the secondary image for a Proca star is wider, the deflection angles are smaller, and these peaks, the structure of the peaks and the centroid, they also change from solution to solution. So although the qualitative behavior is the same, there are slight differences between boson stars and Proca stars, which can also be observable.
Can you make, for example, some smoking gun to discriminate both stars?
Well, I would say so, yes. But then again, all of the limits we are trying to impose for now, of course, this is just a first step, would be on the radius. First thing we want to check is to impose constraints of the radius of boson stars and Proca stars. These limits will be different because the observations are different. So if we are able to impose constraints on the radius, the constraints will be different for boson stars and for Proca stars. And the second constraint we want to do is to impose limits on the orbital period, because we have measured these orbital periods here, of course, with very large error bars, but we have predictions, we have measurements for this orbital period, and this is something that can be directly compared with the orbital periods of boson stars and Proca stars. So this is the two limits we want to impose now. Of course, just as a first step, but more complicated things would come afterwards.
Thank you very much.
Thank you.
So any other question or comment? Okay, if not, let's thank all of the speakers in this session.